Okay, so today we are going to see what happens to Km and Bmax in a competitive inhibition. Okay, to figure out this, you should remember some thumb rules. So, the first rule is about Km, the relation between the Km and the affinity of the substrates, affinity of the substrate for the enzyme. Okay, so the second rule is about Vmax. So the Vmax is never going to go up. It is either going to come down or it is going to stay constant. Okay. Third thing is why Vmax might go down. Vmax can go down only if the total number of enzymes go down. Okay. Okay. So let's discuss about the second rule a little bit more. Why Vmax can never go up? Why Vmax can never go up? This is because whenever we are studying about any kind of enzyme inhibition and substrate kinetics, you should keep in mind one thing, that whatever you may add in this system, you may add extra substrates, you might you may add extra substrates or you may add inhibitors. Okay, you may add extra substrates, you may add inhibitors, but you cannot add extra enzymes from outside to the system. Whatever total enzyme was there initially, okay, there should not be any addition further. So let us suppose there were 100 units of enzyme initially. Whatever happens, you do not add any extra units of enzyme afterwards. Okay, and this thumb rule, let us say this as a thumb rule. Okay, so this thumb rule applies for all the enzyme inhibition and substrate kinetics, whether it is competitive or whether it is non-competitive or whether it is uncompetitive. Okay, no addition of extra enzymes to the system. Okay, so right? You know this curve, right? Michaelis Menten curve. This substrate is in the x-axis and in the y-axis we have the velocity of the reaction, right? So when you increase the concentration of the substrates, at some point the velocity is no more increasing. Why? Because at this position all the enzymes are saturated. All the enzymes in the system are saturated and there is no more addition of the extra enzymes you are doing, right? So this is an assumption that is taken when you are dealing with this kind of enzyme inhibition and substrate kinetics. You don't add any extra enzymes. Okay, otherwise you are going to mess things up. Okay, So this is another one, like you take it as a thumb rule or you take it as a assumption, whatever. Don't add any extra enzymes to the system. Okay, so so what happens is whenever there are, let us suppose, total 100% of the enzymes, 100 units of the enzyme, if all the enzymes are saturated, it is going to reach the Vmax and it is going to form a plateau. It can no more go beyond this, right? Because all the enzymes are now saturated. Okay, okay. So keeping all these things in mind, let's go to our competitive inhibition, right? So in a competitive inhibition, what happens? Let's suppose in any kind of enzymatic reaction, what happens? So enzyme plus substrate, it gives us to enzyme substrate complex, then it gives us to enzyme plus product, right? So in a competitive inhibition, the most important feature is the binding of the enzyme with the inhibitor is reversible. Okay, okay. So when binding of the enzyme with the inhibitor is reversible, the enzyme is not lost. Okay, the enzyme is not lost. So when binding of the enzyme with the inhibitor is irreversible, okay, the enzyme sticks tightly with the enzyme. The inhibitor sticks tightly with the enzyme, and it never comes out, and the enzyme becomes completely non-functional, and the enzyme is lost. Okay, so initially, let us suppose there were 100 units of enzyme. After you add a irreversible inhibitor, let us suppose you added 50 irreversible inhibitors. Now the total number of functional enzymes are the leftover 50 enzyme units. But when there is a reversible inhibitor in the system, then let us suppose there were 100 enzymes in the start, and you add 50 inhibitors, those are reversible. Then what is going to happen? You are still having 100 enzymes, those are function. Okay, so you can see here, no enzymes are lost. Okay, no enzymes are lost. So now if we talk about the Vmax, see, Vmax, first thing is, in a competitive inhibition, no enzymes are lost. Okay, second thing is, let's see the system before and after addition of the inhibitor. So previously there were only enzyme and substrate, and after addition of the inhibitor you are having enzyme, substrate and inhibitors. So previously we are having only enzymes and substrates. So when you are having this kind of system, so both enzyme and substrates are randomly moving in the system. Okay, they are having this Brownian motion. Okay, and whenever they come close to each other, they are able to interact with each other to form this enzyme substrate complex and give rise to product. Okay, and this conversion is happening at a certain rate. Okay, but when you are adding inhibitors, and in case of competitive inhibitor, the inhibitor is reversible. Okay, so when you are adding reversible inhibitor, what is happening is it binds to the enzyme, then it comes out, then it binds to the enzyme and again comes out. Okay, so what happens is whenever this inhibitor is binding to the enzyme, it is not allowing the substrate to bind to the enzyme. It is reducing the chances of the substrate to bind with the enzyme. Okay, so what is happening? the rate is going to come down because the number of times the substrate can bind to the enzyme, the number of chances for the substrate to bind with the enzyme is getting reduced because of the introduction of this reversible reversible inhibitor. Okay, but let us suppose we add more substrates to the system from outside. We add more substrates to the system. Then what's happening? We are increasing the chances of the substrate to bind to the enzyme and give rise to product. So what is happening now? You are going to improve the rate, right? So you are going to improve the rate, but also keep in mind that the number of enzymes at the start was 100, and whenever you're adding substrate, then also it is 100. So all the time it is 100. So however, how much substrate you add, it might go and reach the original Vmax. It might regain the original Vmax, but it is not going to cross beyond the original Vmax. Okay, so what is happening? You're adding substrates, you're increasing the concentration of the substrates. So although at the starting the rate was getting down due to introduction of the inhibitors, now you are introducing more number of substrates than the inhibitors, the Vmax again goes up to the original level, to its original level, but it can't cross the original Vmax, can't go or surpass, it can't go beyond the original Vmax, or it can't surpass the original Vmax because the number of enzyme units are still the same. The ET before adding the inhibitors is, and after adding the inhibitor remains same. So Vmax is also going to remain same. Okay, now let's talk about the Km. So what happens to the Km? What happens to the Km? So I'm not going to rub these systems. Okay, so when there was no inhibitor, the substrate was having all the chance to bind with the enzyme to give this product, right? When you are introducing the inhibitor, the substrate is now having less chance to bind with the enzyme. Let us suppose uh, we are not adding any extra substrates for now. Okay, so what is happening? The substrate is now having less chances to bind with the enzyme because the inhibitor is competing with the substrate to bind with the enzyme. Okay, so what is happening? In this kind of situation, the overall affinity of the substrate, the overall for Km, the overall affinity of the substrate to bind with the enzyme is going down when we are introducing the inhibitor. So based on the relationship we in the first term rule, whenever the affinity is going down, what is going to happen with the Km? The Km is going to rise up. Okay, this is it. Okay, so what happens now in a competitive inhibition? Km goes up and Vmax is constant. Okay, so this is your answer.